Solve problem 3.2, fixed and moving positive charges. A positive charge of 4.50 microcoulomb is fixed in place. A particle of mass 6 gram and charge positive 3 microcoulomb is fired with an initial speed of 66.0 meter per second directly towards the fixed charge from a distance of 4.20 centimeter away. How close does the moving charge get to the fixed charge before it comes to rest and starts moving away from the fixed charge? So here in the question you have a fixed charge. I will call this as QF, which we assume to be placed at the origin x equals 0. And the value of this fixed charge QF is 4.50 microcoulomb, which you can write as 4.50 times 10 to the power negative 6 coulomb. Then you have a particle of mass m equals 6 gram, which will be 6.0 times 10 to the power negative 3 kilogram. And this is a movable charge. So I will write this as Qm. And the value of Qm is positive 3 microcoulomb, which will be 3 times 10 to the power negative 6 coulomb. And it is fired with an initial speed V0 of 66 meter per second. And initially it is at a position, let me call it as T initial of 4.20 centimeter, which will be 0.042 meter. We need to find at what position will it come to rest if it is fired directly at the fixed charge. So we need to find its final position df when the speed becomes 0. Now when the moving charge is fired with an initial velocity v0, it has kinetic energy at this position. And as it moves towards the fixed charge, all of its kinetic energy is eventually converted to potential energy at the point where it stops. So the work done in moving the charge from an initial position of Ti to a final position of Tf is equal to the change in kinetic energy of the charge. So we can write work done is equal to delta K. We know that work done can be written as negative Q delta V, that is equal to delta K. Negative Q delta V is nothing but the potential energy of the moving charge. So this Q I will write as Q for moving, delta V. Delta K you can write as K final minus K initial. K final will be equal to 0 as my final velocity of the moving charge is 0. So that means this term over here becomes 0. And you get negative Qm delta V to be equal to negative K initial. Cancel off the negative sign and you get Qm delta V equals K initial. Now how do we calculate the potential difference delta V? Now delta V is the potential difference between the initial and final position. And I can write delta V to be equal to V final minus V initial. And we know we can calculate V by taking K, Q over R. But which Q are we going to consider here? Now the moving charge Qm is moving in the electric field of the fixed charge. The fixed charge QF is creating electric field around itself. And because of that, you have electric potential at different points near the fixed charge. And since the moving charge is moving inside the field of QF, it experiences these potentials at different points. So when I'm calculating potential difference, this Q over here I have to take for the fixed charge. So we write KQ fixed over the final position df minus KQ fixed over the initial position di. We can take KQF as common and we get delta V to be equal to KQF 1 over T final minus 1 over T initial. Now we will substitute this expression for delta V in our equation over here. So we write Qm. In place of delta V, let's write this K times Qf 1 over D final minus 1 over D initial. Initial kinetic energy I can write as half mv initial squared, which is nothing but v0 square. So I will write my initial speed as v0. Now rewrite this expression. We get k, q fixed, q moving, 1 over d final minus 1 over d initial equals half mv0 squared. Now you can use shift solve at this expression over here to calculate d final if you do not wish to rearrange further, or else we can rearrange and solve for df. So first let us divide by the term over here, and we keep the terms in the bracket as it is. We get 1 over d final minus 1 over d initial equals half mv0 squared over k q fixed q moving. Then we move this to the other side and we get 1 over d final equals, since this is negative, when I move it to the other side it becomes positive. So 1 over d initial plus half mv0 squared over k q fixed q moving. And when you take the reciprocal of this term, you will find the value for d final. I get d final equals 1 over d initial plus half mv0 squared over k q fixed qm inverse. Now let's substitute the values that we have. We get 1 over t initial is 0.042 plus half mass of the charged particle is 6 gram, which is 6 times 10 to the power negative 3 into v squared, so 66 squared over k is 9 times 10 to the power 9. Qf is 4.5 microcoulomb, so 4.5 times 10 to the power negative 6, and Qm is 3 microcoulomb, so 3 times 10 to the power negative 6, the whole thing raised to negative 1. And when you solve this, you get the final position to be equal to 0.007605 meter, or you can write this as 0.761 centimeter. So this is the position at which the moving charge will come to a stop before moving in the opposite direction.